We now return to our regularly scheduled probability. We're going to use the insights we developed last time with orthogonal projections in Hilbert spaces onto closed subspaces to really identify what conditional expectation is. Now remember, as we saw last time, given a Hilbert space, such as, relevant to us, L2 of a probability space, and any closed subspace K of that Hilbert space, there is an orthogonal projection linear transformation, which is Lipschitz continuous with norm 1. In other words, it's an L2 contraction, and it's characterized by either of these two properties. The projection of a vector x is the unique vector z in the subspace, which minimizes the distance from x to z, or equivalently, the projection of x into k is the unique vector in k, which, when subtracted from x, is orthogonal to every vector in k. In other words, if I take x minus the projection of x into k and take the inner product with y, that gives 0 for every vector y in the subspace k. Now let's just rearrange that using the linearity of the dot product. That condition is equivalent to saying that for any vector y in the subspace, the dot product of x with y is the same as the dot product of y with the projection into k of x. In particular, if we were in L2 of a probability space, these inner products are expectations of products. So that says that the expected value of the projection onto k of x times y is the same as the expected value of x times y. And this condition uniquely specifies what this thing pk of x is. Now that should look familiar. In lecture 30.2, we showed that with our fledgling definition of conditional expectation, so far only making sense when we have a partition of the underlying sigma field, the conditional expectation onto that partition sigma field of x satisfies this condition here, which is exactly the same condition we have here, except in this case, the y's that we are allowed to integrate against are those L2 random variables which are measurable with respect to the smaller sigma field generated by that partition. So these two would match up exactly, and we could conclude that in fact this conditional expectation is just the orthogonal projection if that K, that space there, is a closed subspace of this Hilbert space. And it is. If we start with any probability space, and we take a sub-sigma field of the sigma field in question, then L2 of the smaller sigma field is a closed subspace of L2 of the big sigma field. Now, let's be clear, we're making an identification here. This is an abstract object, L2 of this probability space, which means we're taking all of the measurable functions with respect to this sigma field that happen to be square integrable, and then we are taking an equivalence relation and modding out by those that are equal almost everywhere in order to make this an actual norm space. Now that equivalence relation is different from the one over here because this is just a different sigma field, so it's a larger class that we're starting with. There is, however, a natural way to identify this as a subspace of this, and that's what I've written here. We're really thinking of L2 as the set of all of those elements of L2 of the bigger sigma field F that happen to be measurable with respect to the smaller sigma field G. With that identification, we see that this is a subspace and it is closed. So to see that it's a subspace, we just need to check that if I have any two elements, x and y, that are in there, and any two real numbers, alpha and beta, then alpha x plus beta y has to be back in there. Well, if x and y are both G measurable, then of course scalar multiples of them are G measurable, and a sum of G measurable functions is G measurable, and so we at least get closure under the right measurability. And then we also have that, as usual, the L2 norm is a norm, so this is less than or equal to alpha times the L2 norm of x plus beta times the L2 norm of y. And since each of those is finite, that means that this is finite, and so that shows that this is indeed a subspace. Now we need to see that it's a closed subspace in order for our musings on projections to make sense. Well, if xn is a sequence of g measurable functions, and if xn converges to x in L2 of the larger sigma field, then we know, since convergence in L2 implies convergence in probability, and convergence in probability implies the existence of an almost surely convergent subsequence, that there exists a subsequence, x and k, that converges to that same x, or a version of it, almost surely. But measurability is stable under almost sure convergence, and so that follows that x, the limit, is g measurable. And therefore, x, which is an L2 limit, and therefore is L2, is L2, in fact, of the smaller sigma field, which is what we wanted to show. So that is a closed subspace. And that means that on the previous slide, where we had identified that this property held for our putative definition of conditional expectation in that limited context, does indeed exactly match here, and because of the uniqueness of this characterization, we can conclude that this conditional expectation in the context of a countable partition of our sigma field is exactly the orthogonal projection onto this closed subspace. And that leads the way for us to define conditional expectation of any L2 random variable. If I have a probability space and I have an L2 random variable x, and I have a sub-sigma field of the starting sigma field, then the conditional expectation onto that sigma field j of x is defined to be the random variable, the projection into L2 of g measurable functions of that vector x. Now let's be clear about this from the start. This does not tell us how to define this thing as a function, because L2 is not a space of functions, it's a space of equivalence classes of functions, and so this is an element of the space L2 of sigma field G with respect to the probability measure, and that's the only identification we have for what this thing is. Now that means that we know what it is up to an arbitrary set of measure 0, but we should be careful about that when we're thinking about this thing as a random variable. We only ever, as usual, know its value up to an arbitrary set of measure 0. We only know a version of it. Now, if we're in a finite discrete context where the probability measure is discrete and the only set with probability 0 is the empty set, that of course pins things down entirely. So I think it's worth taking a moment to run through this definition and how it works in a very finite context to give some intuition. Partly because this subspace seems very ethereal. What does it even mean that we're just looking at the functions that are measurable with respect to a smaller sigma field? Is that really a smaller subspace? I know that when I encountered this for the first and second and third times, I felt like I didn't really have a handle on what was going on. I hope the following example will make this a little clearer. Let's take our probability space to contain 3 elements. The starting sigma field will just be the set of all subsets, 8 of them in total, and we will consider as our smaller sigma field the sigma field generated by this partition of the probability space. So to be clear, as we know from your homework, that means, or just from direct calculation, that this is the sigma field with 4 elements. The empty set, each of those 2 partition pieces, and the full set, omega. Now, for any finite measure that I want to put on this probability space, L2, L1, LP, they're all going to be the same, just the set of all measurable functions. So on the full space, where we have all subsets allowed, measurable functions are just all functions. L2 of this space with respect to any finite measure is just going to be the set of all functions from 1, 2, 3 into the reals, which means R3. It's the set of all triples of real numbers. But what about with respect to this sigma field? What does L2 of that look like? In other words, we need to figure out what it means for a function from 1, 2, 3 into the reals to be measurable with respect to that smaller sigma field. Well, if x is g-measurable, then that means in particular, for any real number t, the set where x equals t has to be in this set. So in particular, let's see what happens when that t is taken to be whatever value we give x at 1. Notice that the preimage of the set x and 1 under x, of course, contains the number 1. That means that whatever set this is, it has to contain 1. There are only 2 events in this sigma field G that contain 1, this one and this one. So that means that this has to equal either 1, 2, or the whole set 1, 2, 3. But what does that mean? Well, if it's equal to this one, it means that x of 1 equals x of 2. And if it's equal to this one, it means that x of 1 is equal to x of 2 is equal to x of 3. So either way, what we've established is that if x is measurable with respect to this sigma field G, x at 1 and x at 2 have to be equal. Now that's really the only constraint here. And so L2, or whatever you want to call the set of all measurable functions with respect to any finite measure on this probability space, exactly consists of all of those functions of 1, 2, 3 that agree on 1 and 2. Now, if we identify such a function with a column vector in R3, this is, in other words, the set of all vectors that look like x, x, y for 2 real numbers, x and y. That is, this subspace here can be identified with the span of the 2 vectors 1, 1, 0 and 0, 0, 1. On the other hand, the full L2 space of F is just R3, and this is a proper subspace of that. Now, if we don't want to make that identification, how should we call these vectors? This is just the indicator function of the set 1, 2, and this is the indicator function of the set 3. Okay, now how about the orthogonal projection, which we're identifying as the conditional expectation? Well, that's going to depend on precisely which probability measure we choose. Let's go ahead and choose the uniform measure, which assigns probability 1/3 to each of the 3 elements, 1, 2, and 3. Then the expected value of any function x is just going to be 1/3 times x of 1 plus 1/3 times x of 2 plus 1/3 times x of 3. And so the inner product is just given by this usual inner product on R3 scaled by a factor of 1/3. So now we have an inner product, which means we can write down the orthogonal projection. And we can use our formula from linear algebra for what the projection will look like, provided that we start with an orthonormal basis of the subspace. The subspace in question is the span of these 2 vectors, and lo and behold, those 2 vectors are actually orthogonal. But they're not normalized, but that's okay. We can normalize them in the process. The conditional expectation of x given g is the orthogonal projection, which has the following formula: x dotted with u1 over the length of u1 squared times u1 plus x dotted with u2 over the length of u2 squared times u2, where I'm just calling these 2 vectors here u1 and u2. Now, what are those lengths? Those are just the dot product of the vector with itself, and since the dot product is here, it's just 1/3 of the usual Euclidean length. So the usual Euclidean length of this vector here is 2, and this vector is 1, and so that means that this vector down here is 2/3, this vector is 1/3, and notice that those are exactly the probabilities of the sets 1, 2, and 3. And so indeed, this orthogonal projection can be written as the dot product of x with u1, which, thinking of u1 as the function that it actually is, means the expected value of the product of x with the indicator of 1, 2, divided by the probability of the set 1, 2, times the indicator of the set 1, 2, plus the dot product here, which is the expected value of x times the indicator of the singleton 3, divided by the probability of the singleton 3 times the indicator of the singleton 3. And there we have exactly the formula for conditional expectation in this finite partition setting that we developed 2 lectures ago. This is the conditional expectation of x given this event times the indicator of that event, and so on. So we see really concretely, at least in this case, that orthogonal projection does reproduce what we developed intuitively as the conditional expectation. Now we can employ our intuition and facts from analysis, from the orthogonal projection theorem, in order to understand better what conditional expectation actually is. Since orthogonal projection is equivalently defined to be the point in the subspace that is closest to the original point, we can just as well think of conditional expectation of a random variable given g as the unique g measurable random variable that is closest to x. And that is closest exactly in L2 sense. This is a very appealing quantitative notion. Conditional expectation is really just the solution of a least squares minimization problem. Thinking more heuristically, a sigma field G is supposed to represent our information about the world. And so the G measurable function which satisfies this minimization problem is our best guess, in the least squares sense, of the value of the random variable x, given only the information that we have in the sigma field G at this time. We're going to make a lot out of that intuition going forward as we use conditional expectation to study stochastic processes. Before we head in that direction, one deficiency of defining conditional expectation this way as orthogonal projection is it only makes sense on L2, which is where orthogonal projections are defined. It turns out that it can be extended quite easily all the way to L1, as we'll now explore and see. First, we need the following lemma. We showed before that orthogonal projections are L2 contractions. That is, they're Lipschitz continuous maps with Lipschitz norm 1 on L2. Now, our orthogonal projection is only defined on L2, but it turns out that it has the same property. It is a contraction in L1 norm when restricted to L2 functions. That is, if I take the conditional expectation of an L2 random variable and then take the L1 norm of that, that is less than or equal to the L1 norm of the random variable x, which is finite because L2 is contained in L1. Let's prove that right now. In order to simplify notation, let's just set y to be equal to the conditional expectation of x given g. Now I'm going to fix the following function, z, which is the signum of y. That's defined to be 1 if y is positive, minus 1 if y is negative, and 0 if y is 0. Let me write that in a slightly different way. I can write it as y divided by the absolute value of y, except that that ratio doesn't make sense if y is 0, so I just multiply by the indicator that y is not 0. And that gives us exactly what's written here. It also makes it clear that this is a g measurable function because y is g measurable. Now, it's also a bounded function, bounded by 1, and therefore it's an L2 function. So that means that this function z here is in L2 of g, which means we're going to be able to appeal to the inner product definition of orthogonal projections in order to figure out what it is. That is to say, I'd like to compute this L1 norm of y here, but the absolute value of y can be computed as y times the signum of y. Now, y is this conditional expectation. In other words, if we let this L2 space of G be k, y is the orthogonal projection of x into k, and we just established that this signum function is in k. And so we have that property, that key property of conditional expectation / orthogonal projection, that the inner product of these two functions is going to be the same as the inner product of just x with that function which is in k. Okay, now whatever that is, positive or negative number, it is less than or equal to the absolute value of that number, which by the triangle inequality for the integral e is less than or equal to the expected value of the absolute value of x times the signum of y. And since the signum of y in absolute value is less than or equal to 1, again, by the monotonicity of the integral, that's less than or equal to the expected value of the absolute value of x, concluding the proof. Now what that means is that we can actually extend this linear transformation, conditional expectation, to be a contraction on all of L1. The reason for that is a general abstract nonsense theorem called the BLT theorem, or bounded linear transformation theorem. But instead of appealing to that, we'll just write out the details right now because it's really not very hard. That lemma shows that if x is in L2, the conditional expectation is a contraction in L1 norm on L2. Now, L2 of a probability space is dense in L1. That's because we can approximate any L1 random variable by L2 random variables. In fact, we can approximate them by bounded random variables, which are in both L1, L2, and LP for every p, because we're working in a probability space. I can just do a cutoff, x times the indicator that its absolute value is less than or equal to n, that's bounded and in L2. And if I take the difference here between those, which is just x times the indicator of the set where x is bigger than n, well, this inside here converges to 0 almost surely as n goes to infinity because x is L1 and therefore the set where it's infinite in value has measure 0. And also this is always bounded by the fixed function x, which is in L1. Therefore, by the dominated convergence theorem, we get that this difference converges to 0, which says that this cutoff of x converges to x in L1 norm. That density result means that we can now write down the following putative extension of conditional expectation from L2 all the way to L1. If I take an L1 random variable and a sigma field G contained in F, I want to define the conditional expectation of x given G as follows. Right now I only know how to define it for L2 functions. So I'll choose a sequence of L2 random variables that approximates my x. Maybe I'll take this sequence here. It turns out it won't matter which one I choose. I took any approximating sequence of x in L1 norm by L2 random variables, or even bounded ones if I want, and then I'll define the conditional expectation of x given G to be the L1 limit of these conditional expectations. These are just defined to be these orthogonal projections. We know they are nice random variables, and what I need to do is establish that in fact this sequence will converge in L1. And not only will it converge in L1, but it'll converge to something that doesn't care which approximating sequence that I chose. Okay, well, to see that, and to see the uniqueness, which amount to almost the same argument, we're going to use completeness in a fundamental way here. If I take the conditional expectation of any two terms in that sequence and compare them in L1 norm, remember that xn and xm are L2 functions, so the conditional expectation is defined just to be the orthogonal projection, which is a linear transformation. So that's just the same thing as the L1 norm of the conditional expectation of xn minus xm. Now, in the lemma on the previous slide, we showed that that is less than or equal to the L1 norm of xn minus xm. And xn converges in L1, which means that it's certainly an L1 Cauchy sequence. So that goes to 0 as n and m go to infinity. So that shows us, by this inequality here, that the conditional expectation of xn is also an L1 Cauchy sequence. But L1 is a complete metric space, as we've shown, and that means that therefore the limit exists. Great. So for any sequence of L2 random variables xn that approximate x in L1 norm, this sequence of conditional expectations of them converges in L1 to something. But a priori it might depend on which approximating sequence I chose. Actually, it won't. If I take any two approximating sequences of x in L1 sense, then I can repeat exactly the same argument and look at the L1 difference between them after conditional expectation. By linearity, again, that's going to be the same thing as the L1 norm of the conditional expectation of the difference. which by the lemma on the last slide is less than or equal to the L1 norm of the distance between xn and yn. And because xn and yn both approximate the same vector x in L1 sense, that means that this will go to 0 as n goes to infinity. And that gives us our uniqueness as well. So this is well defined. And if you like, you can go through the exact same argument one more time with a few more symbols involved to show that this function of x that I've just defined defines a linear transformation here. That is, if I plug in alpha x plus beta x prime here, then what I get is the conditional expectation of x times alpha plus the conditional expectation of x prime times beta. And moreover, this L1 contraction property will also hold for the limit definition. All of those proofs follow exactly the same outline that we've given here, so I won't write them down any further. But we see now that conditional expectation has a natural extension to L1. And so now we can take the conditional expectation of any L1 random variable given a sigma field, at least in principle, as long as we can compute a limit like this. Of course, computing a limit like that is going to be quite tricky in general, and even if we could, computing the conditional expectation as orthogonal projection is going to rely on our deep understanding of L2 of G, which may not be easy to find a basis of and do explicit computations. So that's really not the way to understand conditional expectation. I do want you to think always in the back of your mind, oh, this is a conditional expectation, I'm just doing orthogonal projection. That intuition will give you a firm hold on what we're doing. But the tools that we need to actually compute conditional expectations are in general a little different. And so let's move forward to develop some of those tools. The first is the one we've already used in L2 context. It actually holds appropriately generalized to the L1 case as well. And we'll call that the averaging property or averaging characterization of conditional expectation. Given our setup now where x is an L1 random variable, the conditional expectation of x given g can be defined as the unique L1 random variable that is g measurable with the following property. If I take any bounded g measurable random variable y, and I take the expected value of x times y, which makes sense because x is L1 and y is bounded, then that's the same as the expected value of y times the conditional expectation. This is exactly the property for L2 that gives the orthogonality condition defining orthogonal projection, except now it doesn't really make sense to talk about orthogonality because our functions are not necessarily in L2. Nevertheless, we can still take these expected values, and this still uniquely pins down what conditional expectation is. To see why, first, note that this condition holds if we know that x is in L2. That's just because of the definition from orthogonal projection and the fact that these vectors y in the bounded functions are L2. In general, the definition of this conditional expectation is an L1 limit of conditional expectations of a limiting sequence of L2 random variables that converges to x in L1, and so we just need to compute a limiting commutative diagram. Since xn converges to x in L1 and y is bounded, xn times y will converge to xy in L1. Similarly, by definition of conditional expectation in this L1 context, the conditional expectation of xn given g converges to the conditional expectation of x given g in L1, and so for the same reason we get this convergence here in L1, again because y is bounded. So that means that the difference of these two terms converges to the difference of these two terms in L1, and if it converges in L1, then its expected value converges as well. However, since xn is in L2, by the projection property, each of these terms is 0, and so that shows this property holds if x is any L1 random variable. Now conversely, we want to show that that uniquely specifies the conditional expectation, and that's just a matter of uniqueness. Suppose that we had two L1 random variables that are g measurable, z1 and z2, that each satisfy this condition here. That is, the expectation of z1y and the expectation of z2y are both the expectation of xy for all bounded g-measurable random variables. Well, then never mind what they're equal to. Since these two are equal to each other for all y, we can subtract those two and see that the expectation of z1 minus z2 times y is equal to 0. And now we can follow an argument just like we did earlier in this lecture. If we take y to be the signum of z1 minus z2 times the indicator of the set where z1 minus z2 is less than or equal to n. This is a function of z1 minus z2 and is therefore g-measurable. It's also bounded because of this cutoff, and so this is a bounded g-measurable function. And therefore, if we plug this function in for that y, we're going to get 0. But the signum of something times that something is the absolute value of that something, and so what we conclude from this is that the expected value of the absolute value of z1 minus z2 cut off appropriately is equal to 0. Now that's true for every n, but by a dominated convergence theorem, just like we had on the last slide, that converges to the expected value of z1 minus z2 in absolute value as n goes to infinity, and that tells us that this is 0, but that says that the L1 norm of z1 minus z2 is 0, from which we conclude that z1 is equal to z2 in L1 sense. And so that does indeed show that there is at most one L1 of g function which satisfies this condition, and since we know that this one does, that concludes the proof of this proposition, characterizing conditional expectation by this averaging property. I'd like to now conclude this lecture by giving a theorem which summarizes all of the main properties of conditional expectation that we're going to use on a daily basis from now on. This property here is of course one of them, but there are a bunch of others that we'll get basically for free from it. And here is that theorem now. The conditional expectation, which we can now, if we want to leave aside the L2 development we went through, can be defined by this averaging property, is a linear transformation from L1 of f measurable functions to L1 of g measurable functions, which has all of the following properties. It is monotone. If I have two random variables, x less than or equal to y almost surely, then their conditional expectations are also so ordered almost surely with respect to the same probability measure. We have a conditional triangle inequality. Pointwise, almost surely, the absolute value of the conditional expectation of x is less than or equal to the conditional expectation of the absolute value of x. We have the averaging property, which we just proved. And there's also a product rule. Don't confuse this with product rule from calculus. If y is any bounded g-measurable function, and I take the conditional expectation of x times y given g, as far as g is concerned, y can be set aside, and that is equal to the conditional expectation of x given g times y. Now this property doesn't exactly pin down conditional expectation, but it is a very useful computational tool. And then finally we have the tower property, which mirrors exactly the tower property for orthogonal projections, and for good reason. If I actually have two subsigma fields, h contained in g contained in f, then if I take the conditional expectation onto the small one followed by the conditional expectation onto the big one, or in the other order, either way, all I'm doing is the conditional expectation onto the small one. Before we get into the proof, let me make one remark from points 1 and 2. First, if m is a constant, then the conditional expectation of m, given any sigma field g, is just m itself, as you can clearly work out. That means, from point 1, that if x is bounded, meaning that x is less than or equal to some constant m almost surely, then the conditional expectation of x given g is also bounded by m almost surely. Combining that with point 2 here, that means that if x is bounded both above and below by m almost surely, then the absolute value of the conditional expectation of x given g is less than or equal to the conditional expectation of the absolute value of x, which is less than or equal to m by 0.1. What that shows is that the supremum of the conditional expectation is less than or equal to the supremum of x. And so just like being an L2 contraction and an L1 contraction, conditional expectation is also an L infinity contraction. So now let's prove these items turn by turn. For item 1, let's start by localizing with respect to an element of G. That is to say, let's take the conditional expectation of x given G and integrate it over a set B in G. Well, using property 3 that we already proved on the previous slide, this expectation, since B is a bounded G-measurable function, is just the expected value of x times the indicator of B. Now, since x is less than or equal to y, almost surely, by the usual monotonicity of the expected value, we get that that's less than or equal to the expected value of y times the indicator of B. And then using 0.3 again, we can transform back to this. So, in order to prove what we want, that is that this is pointwise almost surely less than or equal to that, we just need to show that if you have any L1 random variable, measurable with respect to some sigma field, like these two are, then to show that it is non-negative, it suffices to show that integrating it against the indicator of any measurable set produces a non-negative number. That will suffice by setting z equal to the conditional expectation of y minus x given G. For if we can show that that is non-negative, that by linearity is the same as showing the conclusion that we want. So to see why this suffices, we simply take B to be the set where z is negative. Since z is G-measurable, that is a set in G, and therefore, by this assumption, this must be greater than or equal to 0. But at the same time, z times this indicator function is either 0 or negative, and therefore this expected value must be less than or equal to 0. And so that implies that the expected value of z times that indicator function of the set where z is less than 0 is actually equal to 0. Now, taking negative signs, that means that 0 is equal to the expected value of the negative of z times the indicator function that z is less than 0. But on the set where this indicator function is not 0, z is negative, so that negative sign just gives us the absolute value. This is the expected value of the absolute value of z times the indicator function that z is negative. This is a non-negative function. Its expected value being 0 implies that that function itself must be 0 almost surely. And that is precisely to say that the probability that z is less than 0 is equal to 0, which is what we hoped to demonstrate. So that proves monotonicity, and in particular by taking x equal to 0, that shows that a non-negative random variable has non-negative conditional expectation. On your homework, you're going to explore what happens about strict positivity. Now for point 2, the conditional triangle inequality, we simply apply point 1 to x versus its absolute value. Since both x and negative x are less than or equal to the absolute value of x, therefore by the monotonicity property of point 1, we get that both the conditional expectation of x given G and the conditional expectation of minus x given G are less than or equal to the conditional expectation of the absolute value of x given G. And putting those two together tells us that this or this, which under the right circumstance means the absolute value of the expected value of x given G, is less than or equal to the conditional expectation of the absolute value of x given G, almost surely, which demonstrates point 2. Point 3 was the proposition that we proved beforehand in order to power all of this, so that's done. Now for point 4, the pull-out product rule. We want to show that if y is g measurable, then the conditional expectation of x times y is just the conditional expectation of x times y on the outside. So to prove that, we'll use point 3 once again to characterize the conditional expectation. That's the typical way we'll prove things about conditional expectation. And let's actually take two random variables, y and z, that are both bounded and g measurable, and look at the expected value of the conditional expectation of x times y all times z. We'll just choose to group that with the y and the z together, since y and z are both g measurable and bounded, so is yz, and therefore by point 3, that's just the same thing as the expected value replacing this with x itself. But now let's just apply point 3 with z taken separately as the g measurable function, and that will therefore equal the conditional expectation given g of xy times z inside the expected value. Now subtracting this from this, what that means is that the expected value of this difference here, y times the conditional expectation of x minus the conditional expectation of xy, all times z for any bounded g measurable function z is equal to 0. And now, following the same pattern that we've done twice before in this lecture, we can take z equal to the signum of this, which I'll call u, times the cutoff indicator that it's less than or equal to n, and we'll conclude from there that 0 is equal to the expected value of the absolute value of u times the cutoff indicator for every n, but by the dominated convergence theorem that will converge to the expected value of the absolute value of u, which implies that u is equal to 0 almost surely, which is exactly what we hoped to show. And finally, we are left to prove the tower property, and I'll just say that the tower property is exactly the statement of the tower property for orthogonal projections in the case where x happens to be L2, so all we need to do is extend that to x being in L1, and we'll do that in the way that is, I hope, by now standard to you, by approximating x by a sequence xn in L2 that converges to x in L1, and taking limits of everything in sight, being careful, and I'll leave you to work out the details. Those are the main properties of conditional expectation, and the main ways we'll compute conditional expectations going forward. Next time, we will explore how conditional expectation interfaces with independence.